This is a standard view of a OpenFoam simulation directory. There will be a 0 folder, there will be a constant folder, and there will be a system folder. In 0 folder, we will store the initial condition and boundary condition. These are the conditions that we will apply to the simulation before starting. And in this constant directory, we can see the try surface in which we have stored the obj object exported from Blender. Based on this mesh, we will create the finite volume mesh by using block mesh command and using snappyx mesh command. And these are the fluid properties. This is about gravity, this is about the water properties, kinematic viscosity, density. About water, its kinematic viscosity, density, and the type of fluid, Newtonian fluid, all those things that relates to the fluid. And turbulence properties, here it is considered as laminar. I have taken this case study from the filling of tank tutorial provided by Joseph Nagy. I have given the description in the reference. I highly recommend to learn more about OpenFoam by going through his tutorial. You will get much more information. Here I will just show how to run a multi-phase simulation using this conformal channel using Blender and OpenFoam. So the third folder will be a system folder. In the system folder, the block mesh dict will be responsible for generating the initial mesh, and the control dict where we can control the simulation time, writing the output file in each interval, and we will mention about the Cura number within this control dict. Decompose part dict, it will partition the domain for parallel simulation, either for meshing the geometry or for running the solver. It will create partitions for each processor. And the FE scheme, the FE scheme directory in the system directory sets a numerical scheme for terms such as derivative in equation. Basically, it is about the mathematics that represent in the computer code. So it's about the mathematical side of the simulation, and FE solution is how to process the simulation calculated from this mathematical method. So there will be processing of data that will be handled by FE solution. More on this you can check on this OpenFoam website. It's about the algorithm solution and algorithm control that will be handled by this FE solution. And next is the mesh quality dict. More about the mesh quality dict, that it is an important part of this meshing process, but however I will be just focusing on completing the meshing process. But if you want to make a fine mesh, then you have to concentrate time on this dictionary. So the quality of mesh will be depend mainly on this mesh quality dictionary. And the set field means we will make a particular region of the mesh domain filled with a particular value. Here I will be using this cylinder region. Within the cylinder region, the mesh region will be allotted the value 1. Alpha dot water will have value 1. The remaining region will have 0. I will show in the coming session how to use this set field command. Next is the very important dictionary, that is the snappy hex mesh dictionary. Here we will be defining our parameters in order to create the conformal mesh around this conformal channel. After running this block mesh, we have a hexahedral block, cuboid block, from which we have to define the mesh, finite volume mesh, in order to perform the simulation. That we have to define here. There are a lot of parameters are there, but I will concentrate only few parameters. I have to learn much more, so I'll be just focusing on what all important things is necessary in order to run these conformal channel simulations. So first will be the castellated mesh. It will just create a hexahedral mesh in the shape of the geometry that we stored in the tri-surface. It will be a rough surface, but rough means regular hexahedral mesh assembled together in the shape of the geometry that we have given in the tri-surface folder. In the next step, the meshes will move to the boundary. It will snap to the boundary of this geometry object, so that the end will be a smooth boundary in the shape of the geometry. Add layers will develop the boundary layers. So there will be, from the wall to some distance, there will be the boundary layer where we have to get the correct calculation. So add layers will help in creating the boundary layers. Here I am not showing those process because I was not able to create those add layers in these complex structures. Maybe on a later stage I'll demonstrate how to create add layers in these complex channels. So that is about snappy hex mesh dictionary. It's an important part of this simulation. And surface feature dictionary, it will dictate the edges, sharp edges in this channel.obj or the geometry that we are supplying. It will check for the features in the structures, and based on that the snappy hex mesh will detect the boundaries and split the mesh. Okay, next we can move on to the simulation procedures. The first command is to create the block mesh around this geometry. Before running that command, we have to ensure that the data that we given in the block mesh is in such a way that it is slightly greater than the bounding dimensions of the geometry. For that, in order to check that, we have to just open the para view and have to view the mesh. I'm running this para view in the background, so I will open, and from the constant tri-surface I will click on channel.obj, and if we apply, we can see the mesh that we have imported from the Blender. This is our geometrical object, and from the information tab, if we search for the dimension, these are the dimension, and if we open the block mesh dictionary, we have mentioned the vertex locations that has to be slightly greater than this geometry bounding box dimension in each dimension. So if I click on this block mesh dictionary, in x-axis it is minus 0.1, so in bounding box it has to be slightly more in that direction, that is 1.2. likewise in the positive 0.06, so it is 0.09. everything is in everything is in meters. In the y-axis it has to be 0.1 in block mesh, because here it is 0.07, and in the negative side it has to be 0.1, because on the positive side it has to be 0.1 because it is 0.07, and the z-axis it is 0.04, so slightly greater 0.07, and in the positive side also it is 0.04, so 0.07 in the block mesh dictionary. So everything is okay. We will go for to run the first command, that is block mesh. I will open another terminal, and in that I will type the command block mesh and click enter. cannot find the file system control date. Sorry, we are not enter into the right folder. Backspace. Sorry, we have to move back to one level. In this project directory, we have to call the command block mesh. So I'm running it again. Block mesh. So that's completed successfully. So if we check the constant directory, there will be a polymesh directory. This directory right now will handle the data about the block mesh. So if we open the paraview, before opening the paraview, just create a file within this multimesh folder with the Linux command using touch. Create a file name with extension form. So I have created a file with the extension form.form, and if I open that file, I can visualize the block mesh just now generated. If I click on apply, so this is the block mesh that we have created. So within this block mesh, our geometry should contain. It does not fall along the face, or it does not go out of this block mesh. It should be well within the boundary mesh. So if I make this boundary mesh transparent, you can see our geometry, that is a conformal channel, lie within the boundary mesh. So this is okay, this step is okay. The next step is entering surface features. So it will detect any sharp edges in the geometry, and that data will be used in the snappy hex mesh process. So in this stage, under constant directory within the try surface, a channel.emesh file is generated, which will be utilized by the snappy hex mesh, and also a channel.extend feature edge mesh. So the next command will be to type snappy hex mesh override. Why I am writing the override command is, if we check the system folder, and in this snappy hex mesh dictionary, I have made the castellated mesh true and snapping also true. So override will do, first it will create the castellated mesh, and then it will rewrite the snapped mesh. First the castellated meshing procedure will complete, and in the next step the snapping process will complete. I'm not adding any layers, that's why it is given as false. So if I go for the snappy hex mesh override command and pressing enter, the snappy hex mesh will generate after some time. It will take usually 20 seconds, not usually, for this mesh, and for this given parameters, it will take only a little amount of time. Just wait, we can just wait for the process to complete. And this is the meshing process, the crucial meshing process in this simulation. It has to be fine, but I'm not using these parameters in order to make fine meshing, because it will increase the computing time. So I'm just making a coarse mesh. The process complete within 42.13 seconds. If we open the paraview, if we refresh the data, and if you drag here, now this is the snapped mesh. If I hide the channel.obj, this is our snapped mesh. This is a solid mesh object. We can verify that with, I will increase the opacity. So this is our mesh as coarse mesh because of the computing limitation making it coarse. If we take a plane, if we hide the plane, and if we take the surface with edges command, this is the cross-sectional view of our mesh just now created. Once we complete the snappy hex mesh process, the mesh will confine to the geometry that we have supplied, that is channel.obj. Here in this stage we can see why we have separated different region in Blender, like inlet, wall and outlet. So the channel.obj contain the group data of this inlet, outlet and wall, and while performing this snappy hex mesh process, it will identify this internal mesh will have these three patches will be the boundary of it. So what is the advantage? We can define the input parameters in the 0 folder based on these boundaries. So through the channel inlet the water will enter, and channel wall will be act as the boundary, or it will confine the fluid passing through it, and through the channel outlet the fluid, here it is water, will exit. So for that purpose we have created different patches in Blender and exported in .obj format. And also one more thing you have to check, that in order to get the confined solid mesh after snappy hex mesh process, you have to mention one important parameter in the snappy hex mesh dictionary, that is location in mesh. So in order to check whether the mesh is within the geometry or outside the geometry, you have to verify with this point source. I have mentioned the location in snappy hex mesh dictionary as minus 0.05, 0.03 and 0. Let's check in this with this point source object in ParaView. So I will apply the value as minus 0.95, then 0.03, apply. We can see this will come within the mesh object we given, that is channel.obj. so this thing you have to ensure before calling snappy hex mesh command. If the point is outside this geometry, then the final mesh, solid mesh, will be created or returned in such a way that it will give the mesh such that it will be the remaining of the block mesh minus the geometry we supplied. So that will be of no use. So you have to take care of this point. This is important parameter, that is location in mesh. If it is outside, it will retain only the mesh region, that is the remaining part of the block mesh, that you have to take care. Okay, the next step is setting the field. So we have successfully created a snappy hex mesh. Next the command will be setting the field, the mentioned field, with alpha dot water value equal to 1. For that I am going to type set field with F capital. I am entering that. So if we check the folder 0 and opening this file, we can see that values assigned to the cell is mentioned here. If we check values, 42 cells have alpha dot water value is equal to 1. That we can visualize in ParaView. Just refresh the form.foam object. and if we don't want to skip the 0 time, and if we open this, I'm hiding this sliced view, and open this mesh form.form object with surface view, and if I open the alpha.water, you can see the some region is filled with water. Actually it should be somewhat more, so I will delete it. I will delete the alpha.water again. I'll copy from this 0.ori and I will paste it in 0 folder. This time I will go to system folder, set field dictionary, and I will make that value somewhat inside, towards inside the mesh, and again I will run the set field command. That's also completed. Perfect. Again I will refresh it. You can see that the mesh is filled, much more filled with completely with alpha.water value equal to 1. Okay, so the set field we have set. The next command is decomposing the region into different domains to run parallel simulation. In this case I am using the symbol method, and in the y-axis I will split the domain into two, while the remaining x and z axis it will be normal, it will not divide. Okay, so the next command will be decompose bar, and if I enter this, it will copy the 0 folder data into the processor folders. So if I go to the processor folder 0, and inside that if I type form 2 vtk, again coming back one level, and cd processor 1, again typing form 2. This is just to visualize the partition region, and coming back to one level, if we open the para view and go to this processor 1 vtk, open, apply, this is the domain number 1. Another domain will be in the 0 folder, open, apply, and this is the domain number 2. Domain number 1 for processor 1 and processor 0, processor 1 and processor 0. So this is for doing parallel simulation. The next command will be, in the control dictionary we have mentioned the interform solver in order to perform this multi-phase simulation. So we have given the application as interform, start from 0 time, and end time will be 2 minutes, 2 seconds, not minutes, 2 seconds. But you can give whatever the time you want, but it will take some amount of, if you given 4 seconds, it will take a lot of time to complete. So in order to check the simulation is working perfectly, the inputs are within the control, the simulation is performing okay. In order to check that, initially you have to give a less amount of time, that is, I would say 0.1 second. So within that time we can check whether the simulation is performing in a expected way. Sometimes the main problem that I faced during this simulation is, in the 0 folder there is a velocity folder. In that velocity folder we have to give the input, the channel inlet velocity. So here we have to mention that from the in the inlet phase, the velocity is entering towards the positive x direction. In this direction the velocity is entering. If we check this, the velocity is entering towards the positive x direction. If we are not giving the proper direction, here, the solution will not converge, and we will see a lot of time it will take to complete each section of simulation. So I greatly advise you, before running this simulation, before calling the solver, make sure that the direction of velocity is in the right direction. Otherwise it will not give a good simulation result. How to call the simulation in parallel, how to call the solver in parallel. This is the command mpi run slash hyphen np, the number of solver. What are the number of subdomains we have mentioned in this decompose part dict? Here I mentioned two domains, and I splitted the domains into processor 0 and processor 1, as you saw in the paraview. So that the number that you have to enter here, mpi run 2, then name the solver interform hyphen space hyphen parallel. So if I enter the command, it will start the simulation. So I'm going to enter it. So if everything fine, the simulation will start. So the time step is, this is the time step that you can see here. Right now it is somewhat fast. The reason it is fast, I have made an edit here. Instead of giving Quran number, maximum Quran number 1, I have just given 5. But this is not good for a good simulation. You have to give it as 1. So I am using 5 in order to make the simulation much faster. So the simulation will not be as good as simulation will not be much more closer to the real world, but in this case, to save the computation, I just giving the Quran number as 5. You have to use 1, so the Quran number should stay within this 1. More about Quran number, you can search in the net about OpenFoam and its Quran number, or in wiki you can search it. So the simulation will run until it's whatever the ending time I have mentioned here. It's 2 seconds. It will run until it is 2 seconds. Here the time equal to 2 seconds, then only the simulation will stop. So I am pausing this video here. The simulation run completes. It took around 2516 seconds, around 41 minutes. Now the result is stored in different domains. These are the files that corresponds to each time interval, that is 0.02 seconds. This is for processor 1 and this is for processor 0. In order to combine this result, the next command will be, we have to type reconstruct path. It will join the result from these domains, and we can visualize the end result in paraview after this process. So I am clicking enter. It will combine the data, and it will write the write the file data in this project directory. So it will write every file that corresponds to each time step. So it will go until it writes about all the files, including the file equivalent to 2 seconds. So it will go up to 2 seconds. it is writing. As you can see, the folders are creating. Right now the process ends. Now we can visualize the result in ParaView either by going to the foam.foam file which we have created, or just type parafoam. It will automatically, parafoam command will automatically create a temporary file with extension .foam. So the multiphase demo.openfoam, the extension is .openfoam, not foam. So if we click apply, you can see the 100 time means 0.02, 0.04. So for 2 seconds it will have 100 time steps. So this is the channel wall, which we don't want to show now. We are interested in seeing the result. So just go to alpha.water. This is the node data, this is the element data, and just if we click on this is the time representation for 0, and if we check the 0.02 time, right now it starts the simulation. After 0.02 seconds the fluid will reach here. It will work only if the direction of velocity we have entered is correct. So right now the simulation works fine. We can visualize the result by clicking on this play button. So we can see the time steps moving here. So the water is filling in the channel, and this is the multiphase simulation. And the same procedure you can follow for mode 2 type and mode 3 type. All the parameters for the meshing procedures and the simulation procedures is the same, just change the geometry in the tri-surface folder. That's it. So you can run up to 4 seconds, you can run up to 6 seconds. Also you have to remember that this is a coarse mesh. In order to make a meaningful simulation, you have to refine the mesh much more in detail, and also you have to create the boundary layers. So it will need computation power, so you have to keep that fact in mind. Okay, so this is the end of this simulation tutorial. If you want to know more about OpenFoam and its simulation procedures, I highly recommend the tutorials of Yusuf Nagi in YouTube. Please go through that. Also, I am also learning a little by little about this OpenFoam parameters, mainly about the snappy hex mesh parameters. So in the next videos which are related to OpenFoam, I will make much more clear mesh, and also I will do the computation in cloud system if it is possible. Okay,